In the previous lecture, we have discussed some basic fundamentals of radiation physics. Now, today we are going to start the first concept of this topic, that is radiation physics, and this is actually Kirchhoff's law of radiation. So, first of all, we will know what this law states, and after that we will prove the law and we will see some of its applications. So a statement of this law is very simple. You may see I have written for your convenience the statement here. The statement says at any temperature, let us say temperature T, the ratio of the emissive power, which we denote by the symbol E lambda, to the absorptive power of a body, of any body. If E lambda is the emissive power of a body and A lambda is its absorptive power at a given temperature, let us say T, then the law states that the ratio of this E lambda and A lambda is a constant, and that constant is actually equal to the emissive power of a black body at the same temperature. Here E lambda over A lambda is equal to capital E lambda, and this capital E lambda is what? This is actually the emissive power of a perfect black body at the same temperature, that is the temperature at which our body was. Now, after knowing this simple statement of the law, let us first of all deduce or prove this law. For its proof, let us consider a body A. You see in this figure that this A is a body and it is surrounded by another body, let us say B, which is at a fixed temperature. And now A is our body under consideration. A is body under consideration, and B, this is an enclosure at a fixed temperature. You may say that this is temperature T, it is maintained at fixed. So whenever we will place inside this enclosure the body A, there will be actually energy exchange between A and B, and A will be maintained at the same temperature as that of B in course of time. Now let us consider that E lambda is the emissive power of A, and A lambda is its absorptive power. This is absorptive power of A. We consider it, and T is equal to temperature, which is actually fixed, of B. Enclosure B is maintained at a temperature T. Now, as I have told you, whatever be the initial temperature of the body, it must now be at the temperature of the enclosure. And we consider for calculation an elementary area delta S. See this figure, I have shown in this figure this deep portion. This actually is the elementary surface or elementary area of body A, and this elementary surface area is, let us say, delta S. So delta S equal to an elementary area of A. Elementary area of A. In this condition, if we want to find the radiation emitted per second, that is rate of emission of radiation from this area delta S in a particular direction, say theta phi, then we can find it as I have studied in the basic fundamentals such a concept. So rate of, it means radiation emitting per second, that is called rate. Rate of emission of radiation. Rate of emission of radiation of wavelength lambda by delta S in a direction, say theta phi. See this figure. I have shown the angle theta. In fact, this is normal to the surface delta S. This is normal. And we want to find the rate of emission of radiation in a direction making an angle theta to this normal. And phi is not shown in this figure, but in a spherical polar coordinate, the other coordinate will be actually phi. So in this direction, what will be the rate of emission of radiation of wavelength lambda by this elementary area delta S? We have studied in basic fundamental that this will be equal to what? This is E lambda d lambda delta S cos theta. Actually, this delta cos theta is the component of area vector in direction theta, and d omega, and this d omega is the solid angle. You know, you have studied it in basic fundamental, and so this will be delta S cos theta, and the solid angle bounded by the direction theta and theta plus d theta of phi and phi plus d phi, that is d omega. This solid angle is given by sin theta d theta d phi. This is actually solid angle bounded by the direction theta and theta plus d theta and phi plus d phi. So this is rate of emission of radiation of wavelength lambda by the elementary area delta S in this direction theta phi. Now the total emission of radiation of wavelength lambda by delta S will be what? We can find it by integrating this result for the limits of theta and phi. So therefore we can write rate of total emission, rate of total emission of radiation rate of total emission of radiation of wavelength lambda by delta S. What will be this? Actually, this will be E lambda d lambda delta S integral sine theta times cos theta d theta. The limit of theta will be 0 to pi by 2 and integral of d phi, and its limit is 0 to 2 pi. This is a very simple integral. You can multiply this quantity, that will be 2 sine theta cos theta, that is sine 2 theta, and also divide by 2, and then you can write its integral. So this is a simple integral. I am just writing its value. You can try it yourself. So this will be E lambda d lambda delta S and this integral will be what? This is actually 1 over 2 and this is 2 pi. So what is our result? The rate of total emission of radiation of wavelength lambda by delta S will be pi delta S E lambda d lambda. Here this 2 and 2 will cancel out. So pi delta S E lambda d lambda. Now we can find the rate of total emission of radiation for all wavelengths by delta S. Here our limitation was we have calculated the rate of total emission for particular wavelength lambda. Now we would like to calculate the rate of total emission of radiation of all wavelengths by delta S. Then what will be the result? We will find it by integrating the above result for the wavelength lambda. So the rate of total emission of radiations of all wavelengths by delta S. What will be this? We will integrate the above result with respect to lambda. So this will be pi times delta S integral E lambda d lambda from 0 to infinity. And now we can calculate the rate of total emission of all radiations by the entire surface of the body. Till now we have calculated the total rate of emission of radiations of all wavelength by this elementary surface delta S. But when we will calculate the rate of total emission of radiation for all wavelengths by the whole surface area of the body A, then we will sum up for this delta S, and then we will get the result for the total emission of radiation for all wavelengths for the body A. So we can write a rate, step by step you can see it easily. A rate of total emission total emission of all radiations by the entire surface of the body A. What will be this? This will be equal to summation over all delta S. This delta SS, for all delta S we will sum up it, the above result. So this will be pi times delta S integral 0 to infinity E lambda d lambda. Say this is equation 1. So you have seen how I have calculated the rate of total emission of all radiations. All radiation means radiations of all possible wavelengths by the entire surface of our body A. In fact, here the summation extends over all delta S. Here the summation extends over all delta SS. Now we will calculate the radiation rate of radiation emitted from the enclosure B. For this, see the figure here. We consider an elementary area delta S dash, see this figure, delta S dash of this enclosure B, and this direction is actually the normal to this delta S dash. This is normal. You may see it is normal to delta S dash, and the line joining these two surfaces, elementary surfaces, that is elementary surface of A and elementary surface of B, which is shown by R, makes an angle theta dash to this normal. Now we will calculate the similar term for the enclosure B. For this, let us see here. So now we will consider the rate of emission of radiation of wavelength lambda by this delta S dashed area in a direction theta dashed through unit solid angle. Here we are considering unit solid angle. So rate of emission of radiation of wavelength lambda by delta S dashed in a direction theta dashed through unit solid angle. And what will be this? We write the emissive power of the enclosure by the symbol capital E lambda dashed to differentiate it from a small e lambda, and d lambda as the angle made by the normal to the joining line of S and delta S is theta dashed. So here the projection of area vector will be delta S dashed cos theta dashed, and here we have considered the solid angle d omega to be unity, so here d omega is 1. And as I have told you, this E lambda dashed is what? This is actually emissive power of the wall of the enclosure. This is emissive power of the wall of the enclosure. Now we can find the rate at which energy emitted by delta S dash falls on delta S. And how we can find it? If we multiply the energy emitted by the area delta S in direction theta dash through a unit solid angle by the solid angle made by that delta S area to the site of delta S dash, then actually we will get the rate at which energy emitted by delta S dash will fall on delta S. So therefore you can find rate at which energy emitted by delta S dashed falls on delta S. And what will be this? This will be E lambda dashed d lambda delta S dashed cos theta dashed times solid angle made by this delta S area at the site of delta S dashed. And what will be that? That will be simply delta S cos theta over r square. Here r is the distance between S and S dash. You see in figure, this r is distance between delta S and delta S dash. So you can see how I have found the energy emitted from delta S dash which falls on the surface delta S. Now after this we can find the rate of absorption by delta S out of the energy emitted by delta S dash and falling on delta S. How we can find it? As first of all, see, we have defined the absorptive power in this way. A lambda equal to UA over U. And from this result, what you get? UA is equal to A lambda times U. It means if we have to find the absorbed amount of energy, we simply multiply the incident amount of energy by absorptive power. And so we can easily find how much energy this delta S surface will absorb when the radiation falls from it from delta S dash. So you can find it that so rate of absorption by delta S out of the energy emitted by delta S dashed and falling on delta S, and we will simply multiply the above result by this A lambda, which is actually the absorptive power of this body A, surface of body A. So this will be simply A lambda times E lambda dashed D lambda delta S dashed cos theta dashed times delta S cos theta over R square. And let us rearrange this equation to some extent. Write it A lambda E lambda dashed D lambda. This is delta S cos theta times delta S dashed cos theta dashed over R square. What is this bracketed term? You can see this is simply the solid angle subtended by delta S dashed at the center of delta S. So here say this is equation number 2, and you may say here this delta S dashed cos theta dashed over R square. This is solid angle subtended by delta S dashed at the center of delta S. And what will be this? This will be actually equal to this, and this angle will be same as the elementary solid angle. Elementary solid angle in a direction theta with respect to delta S. Both of these will be same, and so now we can write its value. The solid angle made by delta S in a direction theta is actually what? This is equal to 2 pi sine theta d theta. So let us substitute this value of this quantity in equation 2. So substituting this, what equation 2 will become? Let us see. So you can write therefore rate of absorption of energy by delta S out of energy from delta S dashed. Let us use the value of delta S dashed cos theta dashed by r square, which is 2 pi sin theta d theta. What will be this? This will be simply a lambda e lambda prime d lambda delta S cos theta times 2 pi sin theta d theta. And now we can find the rate of absorption of energy by delta S out of the energy from the entire wall of the enclosure. For this we will integrate this result. So rate of absorption of energy by delta S from the entire wall of the enclosure B. What will be this? This will be simply a lambda e lambda prime d lambda delta S times 2 pi and integral 0 to pi by 2, and this is sin theta cos theta d theta, and you have seen that this integral is 1 over 2. So this will be a lambda e lambda prime d lambda delta S times 2 pi times 1 over 2. This 2 will cancel out, and so the final value of this is pi, you arrange the term, pi a lambda e lambda dashed d lambda delta S. Say this is equation 3. Actually this is the total amount of energy which delta S absorbs from the entire wall of the enclosure B. Now if we want to find out the rate of absorption of energy by entire surface of A, then we will again sum up for this delta S. So now we can find very easily that the rate of absorption of energy by delta S out of the energy from all wavelengths. First of all, we will find this absorption for all wavelengths and then sum up to find the energy absorbed by the whole surface of A. So in this condition we will integrate the above result with respect to lambda, and so this will be actually equal to pi times delta S integral 0 to infinity A lambda E lambda prime d lambda. Now if we will sum up this for delta S, then we will get the rate of absorption of energy by the entire surface of A. So therefore rate of absorption of energy by the entire surface of A out of the total energy from the wall of the enclosure. What will be this? We will sum up for the all delta SS. So this is summation over all delta S pi times delta S and integral 0 to infinity A lambda E lambda dashed d lambda, and say this is equation number 4. Now according to Prevost theory of heat exchange, Prevost theory actually states that the rate of emission and rate of absorption are same, and so according to that theory we can equate the total rate of emission by A and the total rate of absorption by A. So what will be our result? So you may write by Prevost theory. Prevost theory of heat exchange we know that rate of emission is equal to rate of absorption, and so we can equate these two as we have find the total rate of emission by A, and that is equal to see the above results. This is summation over all delta SS pi times delta S integral 0 to infinity E lambda d lambda. And just now we have calculated the total rate of absorption, and that is actually the sum over all delta Sh. Pi times delta S integral 0 to infinity a lambda e lambda prime d lambda. And from this result, what you can get? We simply get that this e lambda is equal to a lambda e lambda dashed, and this implies that e lambda over a lambda is equal to e lambda dashed. Say this is equation 5. So what we see? We see that this result obtained in equation 5 is true for any body, and hence this must also be true for a perfect black body. So if we assume that body A is now a perfect black body, then what will happen? As you know, for a perfect black body, the absorptive power A lambda is 1. And in this condition, we write the small e lambda by capital E lambda. So this result is in fact general. There is no restriction. I have assumed just that A is any body. So if we consider if A is a black body, or you may say perfect black body, then this A lambda will be 1, and we will write this small e lambda equal to capital E lambda. And so in this condition, you may see from this equation 5 that this e lambda will be equal to e lambda dashed. And so we can put in the above equation this very important result, that we can easily see that this is a very important result which we have proved, and from this we conclude that the radiations from the walls of the cavity, is same as that from the surface of a black body, and having the same temperature as that of the cavity, and it does not depend on nature and shape of the wall of the cavity. So in other words, you can say that black body radiation are synonymous with the cavity radiation. And so if we put in equation 5 instead of E dashed lambda, we will write E lambda, then what will be our results? That will be simply Kirchhoff's law. So you can see that we can write it here. Just I am writing it here, that we will put simply E lambda over A lambda equal to E lambda from here. And this is actually what? This is actually Kirchhoff's law. So you have seen that how I have derived or proved the Kirchhoff's law. So following these steps, you can easily understand its deduction.